The topic that we are going to discuss here is multiple hypothesis testing. When we perform hypothesis testing, then the general setup is this. We have two hypotheses, H0 and H1. They are mutually exclusive and exhaustive. And we want to know which one is the true situation. For that, we have some data, and based on data, we want to say whether we accept H0 or we reject H0. So it is something like a binary decision, yes or no. Now, when we do multiple hypothesis testing, then we basically do the same thing multiple times. So here we start not only with just a single pair of hypotheses, but with many hypotheses. Say, in this case, I have shown k hypotheses. So H0, H1 pair, k such pairs. All these things are about some common underlying model. They are not hypotheses about completely different setups. So all of them relate to the same setup. Then again, we are given data, and our aim is to come up with verdicts for each such pair. So for each pair, we want to say either accept or reject. So our final output is a vector of yes, no. Yes, yes, no, 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 yes. Which means the first one I have said accept, etc. So that is what we want to do. Any such procedure is called multiple hypothesis testing. Now, while any decision to say accept or reject, any way to come at a decision is in principle a way of testing a hypothesis. But as we all know, we do not just take any such rule and consider that as a valid test. It is not a meaningful test unless it satisfies certain goodness criteria. Something like probability of type 1 error should be small, probability of type 2 error should be small. We need some goodness criteria to be met before we really call it a meaningful, a sensible test. Well, the same thing happens in case of multiple hypothesis testing also, and it is there that multiple hypothesis testing starts differing from just certain hypothesis tests carried out in parallel. It is something more than carrying out k hypothesis tests in parallel. To understand the concept, we have to know a thing called false discovery. So false discovery is a fancy term which is used to mean rejecting a null hypothesis when it is true. So the null hypothesis is true. In this case, I have said that H0I is true. So some particular null hypothesis is true, but your verdict says that it is false. When that happens, we say that you have made a false discovery in the ith case. The idea is that H0 basically says nothing interesting has happened, and H1 says something interesting has happened. So when you give your verdict in favor of H1, you are basically saying, I have discovered that something new has happened. And when actually nothing new has happened, and you are saying, yes, something new has happened, you have made what is called a false discovery. So that is why the term false discovery. Naturally, you want to keep some kind of a bound on how much false discovery you can make. That is the analog of type 1 error in this case. Now, if we just want to tackle false discovery probability for each one of these hypothesis pair separately, in that case, it will reduce to nothing other than k hypothesis tests done in parallel. But here we want to put some restriction on the overall family of all these tests. And there are a couple of ways of doing that. The first thing is called family-wise error rate. Now, both these things rely on this particular random variable, which is number of false discoveries. So you have got k such hypothesis testing setup, and you have a rule based on your random data. You notice that you have made some false discoveries. Count the number, which is going to be random because it is based on random data. We call that random variable capital N. That is the number of false discoveries that you have made out of k tests of hypothesis. Then you want to have n to be small. Now, how do you tackle this idea of quantifying n should be small? The first thing is called family-wise error rate, that I will often abbreviate as FWER, which simply says probability that n is greater than 1. I have made a little mistake here in this slide, I see. So, it should be probability n greater than or equal to 1. So, n greater than 0. So, even if you make at least one false discovery, that is bad. And you want to keep some bound on this quantity. So, you will say, I will not allow this to go more than 5%. So, that will be something like a size of a test, except that it is not putting a restriction on each of the hypothesis testing separately, but on the overall family. So that is one way of doing it. Now here is another way of doing it. This is called the false discovery rate. Here we look at the false discovery rate, which is meant by basically n upon k. So there are k tests that you made. Out of that you made a particular mistake, namely a false discovery mistake, n times. So the rate is n by k. You take expectation of that and you want to put a bound on this quantity. So you want to say, I do not want to make error on more than 5% of the test. So both these criteria are used in practice. When you have lots of hypotheses to be tested, something like k going from hundreds to thousands, then false discovery rate is the more popular one. But when you have fewer, something that you can count in tens, then family-wise error rate is the more popular one. And in case of linear models, the second situation happens more often, where the number of hypotheses is of the order of tens at most, something like 10 or 20. We generally always use family-wide error rate.